Hi, and welcome to Engineering Physics 3004, topic set number 2, where we talk about the Bernoulli and energy equation in chapter 12. So the Bernoulli equation, the incompressible Bernoulli equation, is this: pressure divided by density plus velocity squared over 2 plus g times z, so 9.81 meters per second squared times z, whatever height we're at, is a constant along what's called a streamline. This full thing is the Bernoulli equation. It's not always valid. We're going to look at the assumptions that are required to derive it later, but this is the incompressible Bernoulli equation. You can see right away what some of the assumptions are. Incompressible flow, meaning density is a constant along the flow and along a streamline, not across streamlines, but along any given streamline. What's a streamline? A streamline is if you imagine flow past something like, maybe this is an airfoil here, then here's some flow. The water that starts here is going to move over here and then over down that way. Could be water, could be air, whatever. Anything that's flowing, any fluid, flows around along these streamlines. Streamlines are just the paths that fluid takes. So this is really much more useful, and it turns out only valid in steady flow, so that we have this concept of a streamline behaving consistently if we look across time. All right, let's look at an example here. So we've got water discharging from a large tank. How fast is V2? So this is a large tank. It's got a big radius up here at the top, large surface area. Water is discharging here. Now to do this, what you should do is set up a streamline from the top and imagine that this particle at the top is flowing eventually out there, like some kind of streamline from there out the side. So you say that's a streamline, or maybe the water that's flowing out the side came on a path from the top, and that means you can look at this point and figure out what the difference in conditions are. So like, what is the height, pressure, and velocity here relative to the height, pressure, and velocity here in order to solve for what you want to solve for. To do that, you're going to say that the velocity at the top is basically 0 compared to this, because it's a large tank, so it's not, draining super fast. If this is if it was, this velocity would be just that much larger, so we can still make that assumption. But it is higher, and since they're both open to atmosphere, then you have the same pressure. And this is a trick you're going to use typically with the Bernoulli equation, to be able to cancel some things by saying that they're the same on each side. So here, at the 2 points we picked up there, and just after it leaves the valve there, or maybe the orifice, the hole at the end, the port at the bottom, then the pressure is the same. So pressure is open to atmosphere on both sides. P1 is P2, so you can cancel those. They're on each side of the equation, so they go away. At the top, the velocity is basically 0, so that's gone. And at the bottom, we're going to define Z as 0, or anyway, the Z on the left-hand side at the top is 5 meters higher than the Z on the right. That gives us the relationship that the velocity that it's leaving with is equal to the root of 2gz. Great. All right, next one. We're going to try to figure out what the water jet height is as a function by knowing the pressure inside the hose, so the pressure at the top of this hose. And this is going to be our point 1, and we'll use point 2 as the top there. Picking the points when using the Bernoulli equation is a lot of the challenge here. Now, see if you can figure out what to sub in. Here's how it goes. The velocity at the bottom is basically 0. The velocity at the top is definitely 0, because that's where it reaches the final point. It stopped moving there. Why is the velocity 0 at the bottom? Because we're looking inside before it's just left. And if we're narrowing the escape point, narrowing the orifice there for it to escape, then it's not going to be much velocity inside compared to the other velocity that's out here. So just before it leaves, we've got a very small velocity, and at the top the velocity is definitively 0, and the height is 0 at the point 1 compared to at the top. So this is whatever distance higher that we're trying to solve for. The only thing that's left is the difference in pressure between the top and the inside of the hose and the top of the jet. Top of the jet's going to be at atmospheric pressure, so we can use this to solve for the pressure inside. We could also have done this to figure out the speed of the jet, if that's what we wanted. So then in that case, the pressure there would be the same as the pressure at the top because they're both open atmosphere, and this would be the jet speed. Dr. Minnick, this Bernoulli equation thing is great. Where does it come from and when is it valid? I'm glad you asked, Jimmy. Deriving the Bernoulli equation. As you can see, we've got a streamline here, and here's our little fluid element. This is a volume ds times dA in the cross-section, and we've got a pressure on this side, a different pressure on this side maybe because that can change along the streamline. We've got some weight W. It's at some angle theta relative to the normal direction, which we also are saying is the, we're going to pull this off to the side and look at the ds there versus dx and dz. There's our variable setup. And let's figure out Newton's second law on this little fluid element. So the force balance along the streamline, some of the forces on this thing would be the little bit of mass that it has times the acceleration in the streamline direction. And acceleration in the streamline direction is the rate of change of the speed. The mass is rho times the little bit of volume, which is ds dA, and the rate of change of speed, dv by dt, by the chain rule is dv by ds times ds by dt. Okay, that's the right-hand side. We're going to leave that the same on the next line and mess around with the force. What is the force on this thing? Let's add it all up. We've got some pressure force. The pda is going to cancel because that's the same on both sides, so it only depends on the change in pressure. dpda, and that is going in the opposite to the streamline direction, negative dpda. Next, we've got the weight. The weight is rho times the volume times g sine of theta in the streamline direction. So negative this because that's, project this onto that section, and we've got weight pushing the little bit of fluid in this flow section of the streamline in the opposite direction to our S direction. Okay, so now we've come up with this line right there for the force balance along the streamline. Next, in steady state, this part's really neat. In steady state, ds by dt, the rate of change of your position with respect to time is what the velocity is. That's the speed. So we're going to replace that ds by dt term with dv by ds. And then v dv by ds is the same thing you would get if you were to take the derivative with respect to s of v squared divided by 2. So v squared divided by 2, take the derivative with respect to s, you'd get 2v times dv by ds. Again, by the chain rule. That thing is really coming in handy. So we got the chain rule on the right-hand side to turn this thing into this. We're also going to drop the dA because that's in every single term. So let's get rid of that. And on the left-hand side, what's going to happen is we will get the sine theta with some trig turned into dz by ds. Up in the triangle here, sine of theta is opposite over hypotenuse. So there we go, dz by ds. Then we also divided out the ds from this term and this term to get it on the denominator over here in dp by ds. Since we had another d by ds show up from the factoring that we did from the chain rule on the right and from the sine substitution for the triangle there for sine theta, we have every term with a d by ds. After we rearrange and put everything on the right-hand side, it looks like this. And then we can integrate, as long as density is constant, to get rid of that and find out that constant integral of 0 is equal to pressure plus rho gz plus rho by 2 v squared. Ta-da! Let's summarize the assumptions of where this is valid. We needed steady flow, so the streamline stays in one spot, and at any one spot, things are constant in time. We needed negligible viscous effects because we ignored the shear force on the sides. There's really some force on the side of each of these things. That would also be in the streamline direction. We needed no shaft work, which means that there's no adding or removing energy along this. We needed incompressible flow. The density needed to be constant. We needed negligible heat transfer, so no other sources of energy. Same thing as the third one when we're talking about work. And, of course, we needed flow along a streamline. What about across a streamline? Well, there's a force balance in the negative normal direction you could do, which would be sort of this direction down here, down and to the right. And if we do that one, we'd have that mass times the normal acceleration, which would be mass times v squared over negative r, now writing dn and dy as two separate things because we're going to need them, where r is the radius of curvature that we happen to be moving in, is equal to, on the other side of the equation, the force balance that we would get from the pressure terms, including a gradient with respect to n, and the weight term that's in the normal direction. Then, cleaning this up a little bit, we can come up with another expression, except this time the trick is going to be things differentiated with respect to n, except that we don't have the same kind of trick for the third one. So we only end up with an indeterminate integral type thing that we can do here. Because the furthest we could take this still involves an integral, it's not going to be as useful as the Bernoulli equation, especially considering how useful it is to look at different places along a streamline rather than laterally across streamlines. So next, static, dynamic, and stagnation pressure. We're going to need to refer to different parts of the Bernoulli equation, now, by the way, multiplied out to be in different units than it was originally. So if we take this thing up here and we go down here and put them beside each other so you can compare, all we've done is multiplied the whole thing by density. And this is the pressure form of the Bernoulli equation. Constant on the right would be a little different. Pressure, P, is the static pressure. It doesn't incorporate any dynamic effects. This is the actual thermodynamic pressure of the fluid. This is the same as the pressure used in thermodynamics and property tables. If you put in the right type of pressure meter, then this is the pressure that you would measure. But I have to be careful because of what we're going to look at next. Sometimes you will actually measure not this if you don't hook up the meter correctly. Next up, this rho v squared over 2 term is called the dynamic pressure. This is an increase in perceived pressure due to the motion of the fluid. So if you put up your pressure meter in the right way, then you'll actually measure this extra force from the impact of the flow at that point, from fluid coming to rest at that point. So this is the pressure rise when the fluid in motion is brought to a stop isentropically. So we have to be careful if you bring the fluid to a stop in a way that generates a lot of heat, then you may not be able to, it may not increase the pressure. It may not give you all of that energy back in the same way that the Bernoulli equation is assuming. Now, finally, rho g z, the last one, is called the hydrostatic pressure. You may recognize this from last time. This is not pressure in a real sense, since its value depends on the reference level that's selected. It accounts for elevation effects. That is, fluid weight on pressure. Be careful of the sign. Unlike hydrostatic pressure, rho gh, which increases with fluid depth h, the hydrostatic pressure term, rho gz, decreases with fluid depth. Now, how does that possibly make sense? Well, as you saw in the previous examples, if we start off with this equals 0 on one side, then the pressure would be higher if Z is higher on the other side. So this is kind of, I mean, it's called the hydrostatic pressure term here, but it is not the hydrostatic pressure that we got in the last section. It's negative that. And even then, that's only if you select the appropriate level of the surface for your Z equals 0 term. So sum of the three is called the total pressure, and the stagnation pressure is the left two. It's the pressure required to bring the fluid to a stop horizontally. So P plus half rho v squared. Remember that the dynamic pressure was the increase in pressure for bringing the fluid to a stop. So the total is the pressure required to bring the fluid to a stop. Together, a piezometer measures static pressure P, and a Pitot tube, which measures the stagnation pressure, can figure out the dynamic pressure and therefore the velocity. So these two pressure meters acting together can determine how fast the fluid is flowing. Fluid flow is going to be the major topic of labs that you're doing this week, the week that we're covering this chapter in the course. So here we go. We've got fluid flow going this way. We want to know what that is. We put this piezometer here. Now this doesn't take advantage of the velocity that's going past to increase the height of the water column, but this one does. Because of the angle of the tube, fluid would flow in here, and here we have a stagnation point. The flow velocity here must be 0 in equilibrium, but because of the angle, we've increased the pressure at this point compared to what we would have had here because we captured the dynamic pressure. So the dynamic pressure is measured by the Pitot tube in addition to the static pressure. So you still get the static pressure and you get the dynamic pressure with this thing. So by looking at the difference in the two, you can figure out what this half rho v squared is. You have to be careful when you hook up a pressure tap like this piezometer here because of the dynamic pressure part. So this one is going to have a higher pressure because you're bringing some flow to a stop here, whereas this one over here is going to have a lower pressure because of the flow down around this way. The stagnation streamline is the one that intersects the stagnation point. In addition to writing the Bernoulli equation in terms of pressure like we did there, you could also write it in terms of head. So here we've got the Bernoulli equation written in terms of z, so kind of like units of distance, units of depth. This is often a very convenient unit to talk about. For instance, in water, we did some work earlier to figure out that per meter, water increases the pressure by 10 kilopascals. So for per meter of depth that you go, you are 10 kilopascals up. If you go 10 meters deep, you are about 1 atmosphere extra in terms of pressure. Sometimes people like to refer to this just by the depth that it would be at for a given pressure. So you can say, oh, there's a pressure there equal to 10 meters of head, or there's a pressure there of 15 meters of head, meaning that it's the same pressure that you would have for a 15 meter depth decrease, or depth increase, 15 meters going down, 10 meters going down. All right, it's not necessarily referring to water, but it would be for whatever fluid you're talking about. Specifically then, this one here is the elevation head. The static pressure head is the first one, P over rho g. That's kind of the static pressure in terms of meters units, or head, P over rho g. And the middle one is the dynamic head. So we have energy head, total. The entire thing is so all of the kind of mechanical energy available, this is the energy head. Second one, static and elevation pressure head, is P over rho g plus z, so everything but dynamic. And this one, v squared over 2g, is called the dynamic head. Now we've given other names to this, the EGL and the HGL. These are the energy grade line and the hydraulic grade line. Let's look at what those are talking about. The energy grade line without any losses would be a constant, and the hydraulic grade line would go up or down depending on how fast the fluid is flowing. So if the speed increases, then it must be because, if energy is constant, either P over rho g or z has decreased. So if the dynamic head has increased, then it must be because the static and or elevation pressure head have decreased. So we can see this in an example in a fluid flow here. This is for a real flow where the energy grade line is decreasing. Energy grade line can only decrease as you go along unless you're adding energy to the system, maybe with a pump. But the hydraulic grade line can go up or down depending on what's happening with the dynamic head. So here we have the hydraulic grade line dropping a lot at the center, and then it looks like it goes up and then back down again. So what's going on here as it rises? Hydraulic grade line must be rising if the energy balance is shifting away from dynamic head. So we have the velocity slowing down, and that's exactly what's going on in a diffuser. Velocity slows down, but you can see the energy grade line is lowering as well. So we are losing energy all along that way. Then there's some thought experiments here. So what do you think should happen to EGL and HGL, energy grade line and hydraulic grade line, for the surface of a lake, etc.? Now, energy grade line is going to be constant whenever the total mechanical energy is staying the same. It's going to increase or decrease if you have gains in mechanical energy or losses. HGL is going to be going up or down in addition to that, depending on what's happening with velocity. So if velocity goes up, then the HGL is going to drop. If velocity drops, then the HGL is going to rise as long as the energy is staying more or less constant. So the surface of a lake, there along the surface, the velocity is 0. We've got constant pressure, constant height. So they're both just going to be constant. And they're going to be equal because there's no velocity in a lake. As the velocity increases and decreases, as it increases, the HGL drops, and as it decreases, the HGL should rise. What EGL will do depends on how it's increasing or decreasing and what's going on with energy. If nothing, then it'll hold still. Ideal Bernoulli flow, EGL should be constant, HGL should rise or drop depending on what velocity does, etc. Okay, so here's an example of some pictures of that. We've got some ideal Bernoulli flow. There is some velocity, which means that the HGL is below the EGL, and then as it constricts and then expands, we return exactly back to before because we did that with no loss of energy. That actually is never going to happen, but ideal Bernoulli flow is kind of an approximation anyway. There's going to be, in reality, some losses along this, and we'll see how to model that with a correction to the Bernoulli equation shortly. Next, here's our pump and turbine. Pump is adding energy, it raises up both lines, and turbine is taking energy out, which is going to drop both lines. All right, this next one is really going to help cement the idea of the HGL. Suppose we're at some surface of a tank here and we go straight down, but the velocity is still 0. What do you think happens to the HGL at this point relative to this lower point? Well, if the velocity is still 0 and we haven't had any losses, then the energy grade line part that is holding energy and velocity is still 0. And with no losses, the other two parts, which are the HGL, should be the same. So with no velocity change, HGL is just constant. Doesn't matter whether we're at the surface of something or looking lower down. But HGL being P over rho G plus Z, as we go down here and then into this part, some of the pressure, the hydrostatic pressure here, gets converted into velocity. If we're at the same depth, then it must be the pressure term that's changing, the pressure head, which is going, so that is static pressure head, that's going into the dynamic head to make this thing move, the part that was the P term going into the V term. And then as you move up, Z is increasing, even though velocity is kind of constant along this, so that must be because pressure is decreasing. And up here at the top, we have some minimum point of pressure, and then as we start going to lower and lower Z's again, the pressure can increase back up to keep this HGL term the same. So if Z goes up, it must be because P goes down if the velocity is holding constant and we don't have any other losses or anything. So let's look at this again. The location of the HGL is actually important because it's in head units. This is the head at the surface in terms of the hydraulic grade line, so the static pressure head plus the elevation head. And then same thing here if we're lower down, but as we go into the maybe inlet here to this section, then the velocity increases, so we have some losses. Then as we move along the flow, there's some more losses, that's why this decreases. Any point where the flow is at a location higher than the HGL, where Z is higher than HGL, which is the sum of P over rho G and Z, must be because P is negative. Look at this. Here we're at a location Z is bigger than P over rho G plus Z. So if Z's bigger than P over rho G plus Z, it must mean P is negative. And that's the thing we can see immediately by plotting our hydraulic grade line along the place where the flow goes up and down. This is telling us where we have to watch out for negative P and where we have to watch out for cavitation. All right, let's learn the physics of stealing gas siphoning. Imagine you have some a car that you definitely own and want to take the gas out of the tank because there's too much in there. So you want to get the gas out of there. So what you do is you put a siphon into the bottom of the gas tank there, and then another end of it into the gas can. Then you have to kind of prime the pump here. I coined that phrase just now. You basically put the whole thing filled up with gas by kind of sucking on this end of it so that it'll get filled up with gas. Then once you've done that, you can lower it into a position where the end here is lower than this end, and that will make it want to flow into this container. It really just needs to be lower than, well, let's see. Should it be lower than this part, or does it just need to be lower than the surface? Let's try a Bernoulli equation example. We'll take this streamline from point 1 around here and then to this end, and you can see that as long as this end is lower than the surface, then we would have a situation where the velocity here must be higher for Bernoulli equation to be satisfied, since they're both at atmospheric pressure. Now, you do have to worry about cavitation. So this can cause a problem, especially at the highest point here, if the pressure drop from all this elevation rise is causing the pressure to go low enough that the constant liquid phase of this thing along the siphon line breaks up. For that, we're going to need to figure out what the pressure is at the top and see if it is below the cavitation pressure of the gas. So basically below the saturation pressure of the gas means it's going to evaporate inside, and this siphon will break. We'll get a pocket of air showing up there, or whatever the gas wants to evaporate into, and then the rest of the line will be able to start collapsing. Bubbles will move along the way, and we'll have to go and reprime the pump or flee the scene, whatever's going on. Anyway, here's the 0.1 relative to 0.2 Bernoulli equation and 0.2 relative to 0.3. Next, final thing to end with is a pitot tube velocity measurement. We talked about this a little bit. If we go from this point to this point, you can take a streamline and see that while the height isn't changing, so it must be that since velocity is changing, the static pressure has to rise at this point. And in terms of head, you can see that exactly is going to translate into the extra height difference on this pressure measurement in the pitot tube versus the static pressure tap over here. That tells you what the dynamic head was, so you can find the velocity. Now you'll note that here, going up to this point, Bernoulli equation doesn't quite work, because from this point to the top here isn't really a streamline. So this is assuming, this is kind of a lateral motion along a streamline, right? So for this to really be a measurement of the velocity that works out extremely well, we're assuming that the velocity inside this tube is more or less constant along the cross section for us to make this calculation.